Good morning, and thanks to the organizer for the nice invitation to this wonderful place. And this talk is also going to be on first passage properties on system of particles with synthesis, very similar to the talk. And this is a joint work with Gabriel Mercado Vasquez. And some more detail can be found in this reference. So one of the paradigm of molecular biology is that gene expression leads to the synthesis of proteins. And through this transcription and translation stage, and physically, proteins can diffuse in the cell or can diffuse even outside of the cell where they are coming from. And they are susceptible to react with binding sites or receptors. And this is very useful for many things like cell-cell communication and for carrying out most physiological functions and homeostasis in general. But in parallel to synthesis, we have the phenomenon of protein degradation, which is also a process which is regulated by the cell or can be also spontaneous. And the lifetime of proteins can vary very widely from minutes to hours. And this is obviously a way of putting a limit on the abundance of proteins in the organism. And it is also a way to regulate spatially the abundance. Like in this Drosophila embryo, where there is a region with a high production rate of transcription factors that diffuse in the embryo, that diffuse a signal slowly. And because of degradation, it is very unlikely to find some functional molecules in this region. And so this naturally produces some gradients that can become stationary and therefore to be some non-equilibrium steady states. And maybe the simplest mathematical model of synthesis and degradation is given by this modified diffusion equation, very simple, with an added loss term due to degradation and a point-like source at some position x naught. So we have this synthesis rate, B, or birth, and degradation or death rate. So these were basically the lambda and mu parameters the previous talk. And quite surprisingly, this model explains a lot of experimental data. Now we know that cellular processes are highly stochastic, that often we have small number of copies of molecules in a single cell, so we cannot talk really about concentrations. And that the movements are stochastic, and then the reaction kinetics can give you as a random search problem involving a certain amount of searchers with a certain amount of receptors in principle. And so this is a discrete stochastic version of the previous equation that we call stochastic synthesis degradation. So SSD, if you want, it's another name for DMR, which on average is the particle density in this model on average is equivalent to the is given by the previous equation, but only on average. So here we basically have, okay. So we have birth or particles that are synthesized with a rate B. They diffuse during a certain time, which is randomly distributed, exponentially distributed, and governed by the degradation rate D. The particles are independent. Okay, so what is well known is the distribution of the number of particles in the system. So there can be at the same time 0, 1, 2, or m particles, and the particle number distribution is given by Poisson distribution with mean B by D. And there is a connection with this problem with actually queuing theory, where particles can be seen as customers that are at some place at random times. They are served during a random time, and then they exit the system. and there is an infinite number of servers. So as soon as a particle enters the system, it is immediately served. Actually, so there is no limit on the number of particles that can be in the system. And actually, the full time-dependent probability can be a quite complicated function depending on the initial condition. So the reaction kinetics. So we assume that at time t equals 0, we have one particle starting at x naught, starting to diffusing, and then all the following particles. So the central quantity is first passage, the probability that no reaction has occurred at up to time t in the interval 0t. That is to say, we assume that this particle is susceptible to react with a target site, which is here in the origin, and space can be 1D, 2D, or 3D. So this is a connection with extreme value statistic, maybe like any or many first passage time problem. So if the particle do not have reacted at time t, it is because it is equivalent, for so it is based in 1D, that the minimum position reached by all this bunch of particles, x min, up to time t, is larger than the target coordinate. The more well-known connection is that if a reaction does not happen at time t, it means that the first passage time, so the first particle that reach the target, will do so at a time t1, the first passage time, larger than t. Therefore, we have this general relation with where p is first passage time density. And the question that one can ask is, at late time, what would be the decay of q of t as t goes to infinity? Is it exponential? If so, what would be the characteristic time of the reaction, tau? Or what is the average, the mean first passage time? So the average of that quantity t1, which defines the second time scale in the problem, which is given by this general relationship, which in general requires the knowledge of the full function q of t, not only the asymptotic behavior. So there is a problem where the answer to the question is very well known and which is quite related to the present problem, which is stochastic resetting. So in stochastic resetting, we have one particle that, as mentioned in the previous talk as well, that diffuse and which is susceptible to reset at random times with some rate r to the origin, and then resume its diffusion with a piece of trajectory which is independent of the first p. And it turns out that the Fokker-Planck equation that describes the position distribution of the particle is given exactly by the same equation as the synthesis and degradation problem, except that B and D are equal to R, the resetting rate. But of course, the two problems are very different because here we don't have a fluctuation in the number of particles. You have exactly one particle in the system, so the distribution is trivial. And in a queuing theory, if you're using a Kendall notation, that would be equivalent to assume that we have only one server. So it's one particle at a time. And once the client is done, the following client comes in immediately, which is possible if the arrival rate of client is very low. So the aim is essentially adapt methods that are used in stochastic into this new problem. In the last 15 years, maybe there are close to 1,000 papers on resetting or related to resetting. And maybe one of the lessons that we have is we can consider something very general, forget a little bit about the diffusion equation, Brownian motion, and consider any process, any spatial dimension, or any geometry in principle. And try to, for instance, address this specific question regarding the optimization problems. Also comparison with single particle standard search problem with one single particle with infinite lifetime, and to determine whether there are some kind of universal features in this kind of processes, which follows from the generality of the description. So the idea of a possible derivation is to consider, so we have the first particle that starts at t equals 0, and that has a certain probability of not reacting with the target because it decays and does not find the target within certain time. At time t, it may, which is observation time, the particle has not found the target and has decayed, or is still alive, but he hasn't found the target, hasn't found the target either. And then there is a second particle, and then all the following particles. So one can notice that because of the independence of the trajectories, the no-reaction probability of all this process is given by the product of this single particle problem, and plus the no-reaction probability of this red process, which is here. And we can notice that this red process is actually a SSD process, but with 0 particle initially. So the problem with one particle initially can be expressed at these products. And then the Q0 process can itself be seen as a Q1 process, but which starts at a later time t minus t prime positive instead of t equals to 0. This is written here. Basically, nothing happened during a time interval t minus t prime. There is a birth that occurs with b t prime probability, and then during the remaining time t prime, the process does not react. And this first term is due to the possibility that no particle is born during 0 and t. So this is basically a closed system, and the input is essentially this probability QD. So QD is analogous to the S of the previous talk. So it's a no reaction probability of a single particle with degradation. So basically, do not contribute to this probability, the trajectory that finds the target in the time less than t, and that have survived. So this is taken into account in this expression. And P0 is a first passage time density of a single particle without degradation. So the standard first passage problem for one single particle. And under a different form, so this is the expression that one obtained, which is similar to the one we have seen in the previous talk. And also that has been derived in some particular case, d equals 0 in these references as well. And it is also possible to calculate, for instance, the joint other quantity that give more information, like the joint distribution of the first passage density, and the total number of particles that has been used until the first passage time. So let's say the amount of the number of searchers that were involved in the search until the first passage time, which is given by this expression and can be useful for to calculate certain quantities. So a first conclusion is that SSD searches are completed in a finite time, and that the decay of Q is exponential, and the characteristic time is inversely proportional to B, which maybe is natural. So the higher the birth rate, the lower faster the reaction, and all the details of the particular case to be considered is encoded in this Laplace transform of the survival probability of the first passage time density of the single particle, evaluated at the Laplace variable d. And the mean first passage time is more complicated in principle, but it's obviously finite because of the exponential decay. So the simple example is a Brownian motion on the infinite line, for which we know that first passage time are infinite. So Brownian motion is not very efficient search process because tail of the survival probability decays as a power law with an exponent which is smaller than 1. And as soon as b different from 0, all this quantity becomes finite and the survival probability becomes exponential. So this is similar to resetting. Resetting, one of the motivations to study this type of problem is that they represent some kind of efficient search strategies. So these are the expression in this Brownian example for the first passage, for the characteristic reaction time, tau, and the mean first passage time is more complicated, but can be obtained in the limit b goes to 0 or b goes to infinity. Actually, I think that this is the lower bound of the previous talk. So fixing d and taking b goes to infinity. And so this is as b goes to 0, so very slow synthesis. These two characteristic time are more or less the same, but at very high production rates, these two time differs very widely because here the decay is essentially 1 over log b instead of 1 over b. And the first passage time becomes a Gumbel distribution. So as noted in this reference, so essentially the problem here becomes similar to many independent and identical particles that start at t equals 0 from the origin and diffuse. So the first passage time is that of the fastest particle. But if b is different from infinite, is finite, the distribution is more complicated. So it becomes a non-standard extreme passage, extreme statistic problem. And essentially the explanation given here, and I see there will be a talk later this week on this, is that the random variables are not identically distributed and they are not independent neither. So, but this has important consequences regarding the minimization of the search cost. So assume that we fix the degradation rate, so it is what it is, and what can we, and vary b, the synthesis rate. So in this example with Brownian dynamics, so b goes to infinity is optimal. So because the first passage, mean first passage time, or the quantity tau becomes very small, but obviously it's very costly. So for instance, transcription is performed by molecular motors, and it takes time, it takes energy. So we can, they are fueled by ATP molecules, etc. So we can define a total cost function, which would try to be a trade-off between the time needed for search and the energy which is required to perform that search, where lambda is some kind of penalty for each particle which is synthesized. And so thanks to this simple relationship, so we count only, so we take the average n, where n is the number of particles created until the first passage time. And that quantity diverges as 1 over b when b goes to 0, and with nearly linear in b for large b, and this log b factor is the previous, that of the previous slide. And as a very simple approximation, we can deduce some kind of optimal degradation rate, which is roughly proportional to 1 over the square root of lambda in the 1D Brownian particle example in the semi-infinite space. Okay, so another question we can ask in a quite different setting is when a SSD process improves a single particle search process. So assume now, okay, we ignore the synthesis cost for simplicity. So we have the standard first passage problem, starting position, a target, for instance, a bounded domain. So the first passage time, we assume that it has a finite mean and a finite variance, so we can form this coefficient of variation CV. And what has been quite useful in recent studies is to perform some perturbative analysis of this kind of this reference problem. And here what we can do is introduce a little bit of degradation of the particle and a little bit of synthesis as well, and perform some expansion of the mean first passage time in the small parameter B and D until to first order. And then we have the following question. So we have a fixed degradation, and we like to know what is the minimum amount of synthesis that is required so that the mean first passage time is equal or slower or lower than T naught, that of the original process. So how can I compensate mortality? By creating new particles. And so this defines critical synthesis rate. So if we wish that the SSD process to be faster than the original process, we need to pay the price that the synthesis rate is larger than the critical value, which is given by this general formula, which is completely universal. So it doesn't depend on the type of process, the type of search process. So it can be diffusion, can be any process that you want, run and tumble motion, so anomalous diffusion, etc., in any spatial dimension. And essentially, it depends, if you know the quantity T naught and CV naught, then you have this simple relation. So this can be calculated or determined numerically. They are related to the single particle search process. So it's completely universal. And what we see that at small d, the BC is much larger than d. So if you compensation is kind of costly. If you want to, the particles must be created at a much higher rate than they are degraded, that they are removed, in order to compensate for the removal of particles. So we wanted to check this relationship with a very simple example, so maybe the simplest one in a bounded domain. So it's a 1D Brownian particle in an interval. You have two absorbing boundaries. So this first passage time problem is very well known. So we have the full pin function first passage time distribution, which is an infinite sum of exponential. We can plug it in the expression for Q1, integrate, take the integrate and deduce the mean first passage for SSD. And then see when this is larger than T naught, which is also known analytically. And we see that the results follow very well this universal prediction of the critical. So above this curve, so SSD is faster than the original process, and below it is slower. And we can check actually that in this particular example, in these units, the reaction, the synthesis rate, critical synthesis rate, is much larger than the degradation rate. So, well, the conclusion, so diffusion under stochastic synthesis and degradation has many biophysical applications and also other applications that have been mentioned. There are some analogy up to some point with resetting processes. And in particular, also foundation can be quite general and some universal results can be derived. And there are some kind of non-trivial optimization property if we take into account some more realistic setting. So there are many other expansions, some of them have been mentioned previously. So how to extend, for instance, these processes to non-Markov synthesis, non-constant rate synthesis or degradation even, some negative feedback loop, so where the particle that are synthesized can react with some inhibitor sites, which inhibits their own production, so which is very common in gene regulation, and study other transport process, etc. So thank you for your attention, and if you have any questions.
Time for a couple questions. So what would happen? Do you really work on the non-Markov synthesis processes?
Not on this non-Markov synthesis. No, not yet. But for instance, the simplest extension is that assume that genes, for instance, are busy during some time, and when they start to produce, they are synthesizing mRNA or proteins, and therefore no initiation can be started during a certain amount of time, right? So you have a lag period, or you can have periodic synthesis, for instance, which is another case of non-Markov synthesis. And of course, they will put this a bound on the mean first passage time. They cannot go in principle down to zero because you cannot go infinitely fast in the production of particles.
Yeah. So in your first slide, the motivation was that perhaps these things would create a gradient in the cell.
Yeah.
How is that happening? How is that gradient happening?
Okay, so that's a combination of synthesis, diffusion, and degradation. So actually, the modified diffusion equation, which is basically this one, except that B and D are different, has a steady state solution. So you can put the time derivative equal to 0, and there are some solutions which are essentially exponentials.
One end, target at the other.
Okay. So if there is no target, if it's just steady state, you just diffuse and degrade by just degradation, not by reacting with the targets. And I guess that if there is a target, it should be kind of similar solutions. And yeah, there are Bessel function solution of this kind of equation. So it's a steady state. And actually, the convergence to the steady state is actually non-trivial. As shown by these people in resetting. Yeah. So that's naturally produce some gradients.
Good. Let's thank Denis again.